Welcome to a lesson on parametric equations. In this lesson, we're just going to look at the basics of parametric equations, just introducing what they are, what they look like. Look at how we can create a table of values and then sketch the graph of parametric equations, and then we'll look at how we can eliminate the parameter, or in other words, how do we convert it from a parametric equation to a rectangular equation. So just to kind of try and introduce the idea here, we talked about in our project the path of a satellite. But if you'll remember, we only looked at the latitude portion of the satellite's position. So what we want to look at right now is how do we actually figure out the position of the satellite? Okay, what do we need? So obviously we're going to need latitude and longitude, not just latitude, but both of them. And we need to know at what point in time it's located there. So let's just look at this GeoGebra activity. Okay, so this is just sort of a generic path of a satellite based off of a sine regression like we did in our project. And right now it has a longitude of 0 and then a latitude of 72.5 degrees north, and we're going to assume this is time equals 0. So as we start moving forward in time, what's going to happen? Okay, so notice we're getting time values in the first column. We're getting x coordinates or longitudes in the second column, and then we are getting latitude values in the third column. Okay, so over time, so at any point in time t, we can determine not only its latitude but also its longitude. Okay, so we actually have two variables that we have to deal with, and both of those variables depend on time. Okay, and so we're going to have one function. We could come up with one function that represents the x coordinate, the longitude. We could come up with another function that represents the y coordinate, which is its latitude. Okay, so we're going to have two functions, one for x, one for y, and both of them depend on time. Okay, so that's the basic idea of a parametric equation. All right, so going back to our lesson, let's sort of give a formal definition for parametric equations. So the parametric equations represent the set of all the points, the x and y coordinates, that form a curve, just like our satellite path. They are defined by parametric equations. So we have a function for x, so x is a function f of t, and y is a function g of t. So the f function and the g function are different. Okay, so one function tells us the x position, one function tells us the y position. And notice both of these functions are functions of t, or of, in the example of the satellite, that was time. It doesn't have to be, but often is. In general, we call t the parameter, and so that's where we get the name parametric equation. So parametric, its root word is parameter. Now, parametric equations, yes, the x and the y coordinates are dependent are our functions, but as a whole, parametric equations do not have to satisfy what we normally think of as a function. So, for example, they don't have to satisfy the vertical line test. And then they don't always go from left to right. So normally when we graph a function, we go always from left to right, so increasing x values. That doesn't have to happen because we're doing increasing t values. All right, so we have to talk about the direction that we're going to draw a curve, or the direction that it's generated. So we think of a positive or forward direction as a positive orientation, or a forward direction. That occurs when t increases. So as t goes from 0 to 10, that would be the positive direction. All right, so let's look at a few examples here. So we have a parametric equation of two linear functions. So x equals 3t plus 2 and y equals a negative 2t plus 5. Now we could look at this for any values of t, but just for simplicity's sake for this example, let's just look at t from 0 to 3. So what I want us to do is we need to be able to create a table of values. So if you remember, probably in pre-algebra, pre-calculus, doing like an x and a y column table. So we're going to do the same thing, but now we're going to have a t column and an x column and a y column. Okay, so I'm going to pick t values from 0 to 3, and I'm just going to go by whole numbers. I could do fractions and decimals in between, but just again, this is a pretty simple example. So we'll go from 0 to 3 by ones. I'm going to take the 0 and plug it into the t for the x coordinate. So 3 times 0 plus 2 is equal to 2. I'm going to take that 0 and put it in for t for the y. So negative 2 times 0 plus 5 is just equal to 5. So if I take this x coordinate and this y coordinate, that gives me a coordinate pair, the 2, 5. And so I can take that 2, 5 and plot it on the graph. And if I repeat the process for the 1, 2, and 3, I get 4 coordinates here that we can take and put them on the graph. So here's 2, 5, 5, 3, 8, 1, and 11, negative 1. And so if we connect those dots, it creates a line. And I've drawn little arrows on here. There's two little arrows. So the way so t goes from 0 to 3, that's an increasing values of t. So the 0.25 is the beginning, and it's going forward towards the 11, negative 1. So it starts here at the 2, 5, and it's moving towards, in a positive orientation, towards the 11, negative 1. So that's what the graph would look like for t from 0 to 3. Now again, we could do any values of t from negative infinity to positive infinity. So this does actually represent the entire line for all the values of t. And also notice that t is not part of the graph. Okay, t is not, there's no t-axis. The t is what we use to determine the x and the y coordinates. All right, let's look at another example. We have x equals t plus 4 and y equals a negative t squared plus 3t plus 4. This time let's go from negative 2 to 3. So we're going to do the same process. We're going to take our negative 2 to 3, and I'll just go by whole numbers. We plug that into the x equation and into the y equation, and so we get these resulting values, and pairing them together we get coordinates. We take those coordinates and we plot them. So we just plot all these points, and then we connect the dots and we draw little arrows to represent the direction. So the point started here down here at 2, negative 10, and it moves up the parabola. There's a parabola here, and then it moves back down. So that's the forward orientation, or the positive orientation. Let's try one more. So in this example, we have x is t to the third minus 4t, and y is t squared plus 1. And again, we'll just do from negative 3 to positive 3. Again, we could go everywhere, but so notice this graph turns out to be a little different. We follow the same process, just plugging negative 3 to positive 3, going by whole numbers, plug them into the x equation and the y equation, and come up with our x, y coordinates. And then we plot them. And so notice with this particular curve, it kind of loops back in on itself. And so it has this portion here where this would not normally satisfy a function, okay, because it would fail the vertical line test. But it still works as a parametric equation. So that's one thing that's nice about parametric equations, is we can get some very different graphs than what you're used to seeing. Now, originally, the x function and the y function, those are functions. But together, the parametric equation does not have to satisfy that function definition that we thought of back in pre-calculus. All right, so how do we eliminate the parameter? So eliminating the parameter is just a phrase where we're trying to get rid of the t in the equation, okay? And so we want to express, we want to be able to figure out a single function that represents the parametric equation. So we're converting it from parametric equations to a rectangular function. So if we had an x function and a y function, both functions of t, we're trying to write it as a single function where either y is a function of x or x is a function of y. And you can go either direction. Usually we like to do the y as a function of x. Sometimes it just depends on how simple the function is. So here are a couple examples similar to what we've looked at already. This first one, both the x and the y coordinates are linear, so it would actually be pretty easy to solve either way. So let's do it first, kind of solving it for y. So take the x equation and solve it for t, and then once you've solved it for t, take that and plug it into the t's for the y equation. And technically at this point here, y equals negative 6 times the quantity x minus 2 over 3 plus 5. That is a rectangular equation. We have eliminated the parameter, but we can go ahead and simplify it down, and we get this linear equation here. And again, this one is pretty easy. We could do it in the reverse. We could take the y equation, solve it for t, and then once we do that, plug it into the x equation and simplify. So again, here we get another linear equation. And if you compare these two, they're the same equation, just this is solved for y and this one is solved for x. We look at the second example here. This one's going to be a little harder. It would not be, it's possible and it would not be too hard, but I don't want to solve the y equation. So we're only going to do this one direction. So we're going to solve the x equation for t, plug that into the quadratic equation for y, and then we can simplify it out. And I started the one here, the second equation. This is technically would be a correct answer because you have eliminated t at this point. And so it's not really necessary to actually simplify it. But I did just so you could see what it would look like. All right, now we want to look at a couple more examples that are just a little bit more complicated. So this first function, we have an exponential function and then we have a linear function. We could do this either way. So if we solve first for the x coordinate, so take the x equation, we want to solve it for t. That's going to involve using some logarithms, and then we can pull the t out front because it's a power, so those are properties of logarithms. We could have simplified things and just done a log base 2, but we'll do it this way. So we get we solve it for t. We take this t expression and we plug it into our y equation. So 7 plus 4t, we replace the t with our natural log expressions. And I didn't show it all here, but it is possible to solve this for x as well. You're just going to have to, we're going to solve the y equation for t and then plug it into the x equation. All right, and then doing our second example here, x equals 5 natural log of t, and y equals 7 natural log of t. We can solve this one again both ways, but so if we let's solve it first for x. So we take x equals 5 natural log of t, we divide the 5 over. To cancel the e, or the natural log, we use the e base, so e to the x over 5 will be equal to t. We take that and we plug it into the y equation in place of the t, and then notice that the natural log and the e will cancel. So again, this should be a review for you from your pre-calculus. So it turns out that y equals 7/5 x. If we would have done it in reverse, it would have been the same process, but we would have gotten x equals 5/7 y. So if you want, you can go ahead and take a look at page 43 in your lab manual. There's a bunch of examples there you can work through. And then when you're done, there's one more thing we can look at. So what if we want to take a rectangular equation and convert it to a parametric? There's lots of ways we can do that, but the easiest way is just to say x is equal to t or y is equal to t. Okay, so let's just look at two examples here. We have y equals x squared minus 5x plus 2. So if I take this equation, so notice y depends on x. If I say x is equal to t, then what's y become? So if x is equal to t, y just turns out to be t squared minus 5t plus 2. I'm just taking all the x's and replacing them with t. So this took the quadratic function that we had, a rectangular function, and it now converts it to a parametric equation. Okay, that's sort of the easiest way. There's lots of other ways we could do it as well. If we look at the second example here, x equals y squared plus the natural log of y, notice that this one's solved for x. It would be really hard to solve this for y, so we don't want to do that. So instead, in this example, let y equal to t. So if y is equal to t, then we have x equals t squared plus natural log of t. So we've been able to convert it very easily to parametric equations. All right, that's it for now. Take a look at your lab manual, practice problems there, and then you should be able to get started on web assignment.